On an ordinary morning along Java's southern coast, everything appears calm. Fishermen set out, markets open, life continues as usual. But scientists monitoring the Sunda Megathrust have just uncovered strange seismic signals beneath these waters, an ominous sign along a fault responsible for over 230,000 deaths in 2004. Why is this 1,000-kilometer silent segment now drawing urgent attention, and could the next megaquake strike within this decade? The evidence is mounting, but what it means for Java's future is a question no one can afford to ignore. Before sunrise, the shoreline of southern Java stirs with quiet purpose. Fishing boats painted in fading blues and reds push away from the sand, nets piled high and engines coughing to life. Along the narrow lanes just above the tide line, vendors set up wooden stalls, arranging baskets of shrimp and fresh mackerel caught hours earlier. Children chase stray chickens between the stalls, while elders sweep the night sand from their porches. For thousands of families in villages like Pangandaran and Pasitan, the ocean is both a provider and a constant companion. Each day begins with the same ritual: checking the sky, the waves, the feel of the ground beneath their feet. Densely populated, the coast here is crowded. Houses and warongs press close to the water, sometimes only a few meters above sea level. Most people cannot imagine living anywhere else. Their livelihoods depend on the sea's rhythms. When the catch is good, the whole village eats well. When storms roll in, or when the ocean pulls away without warning, memories resurface of past disasters and near misses. Many remember stories from older relatives about strange tides and the distant roar of waves, but for most, the threat remains invisible, tucked beneath the ordinary routines of daily life. In these communities, risk is woven into every decision. Some families have evacuation plans taped inside their front doors. Others trust their instincts, watching for sudden changes in the water. The sense of vulnerability is not abstract. It is lived, felt in the creak of bamboo walls during tremors, or the anxious glances exchanged when the ground shakes a little too long. Here, the boundary between normal life and disaster can be as thin as the sand underfoot. Every day, people build, fish, and raise families in the shadow of a fault line that, for now, remains silent. On December 26, 2004, the Indian Ocean shook with a force that stunned the world. At 7:58 a.m. local time, a magnitude 9.1 earthquake ruptured more than 1,300 kilometers of the Sunda Megathrust off northern Sumatra. The rupture unleashed a tsunami that raced outward at jetliner speed, reaching the coasts of Indonesia, Thailand, Sri Lanka, India, and beyond. In less than 2 hours, waves as high as 30 meters struck Aceh, flattening entire towns. The death toll climbed past 230,000 across 14 countries, making it one of the deadliest disasters in recorded history. Even in Java, hundreds of kilometers from the epicenter, people felt the ground sway and watched the sea behave strangely. In some southern villages, the ocean pulled back, exposing reefs and fish on the sand, a warning that only a few recognized. Survivors recall the roar of the approaching water, the confusion, and the desperate rush to higher ground. One fisherman from Cilacap later said he saw the sea disappear. His father grabbed his arm and they ran. The wave destroyed their boat and their home, but they survived. The scale of loss forced a reckoning. Indonesia and its neighbors, caught unprepared, began building the Indian Ocean Tsunami Warning System, installing seismic sensors, ocean buoys, and public sirens. Governments rewrote disaster plans, and scientists accelerated the study of subduction zones. For coastal communities along the Sunda Megathrust, the 2004 event shattered any illusion that the fault's silence meant safety. It became clear that vigilance was not a choice, but a necessity. South of Java, beneath the Indian Ocean, a vast stretch of the Sunda Megathrust sits in silence. This segment, running roughly 1,000 kilometers from the Sunda Strait to the waters off Bali, has not produced a major earthquake in living memory. Unlike other parts of the fault that rupture every century or two, this zone has remained locked for at least 300 to 600 years, quietly storing strain as the Indo-Australian plate pushes beneath Eurasia. Satellite geodesy and GPS networks confirm that the fault here is highly coupled, meaning the plates are stuck together, moving only a few centimeters each year, and releasing almost none of that energy through small quakes or steady creep. Geological evidence along Java's southern coast tells a story of rare but powerful events. Raised coral terraces and sudden coastal uplifts mark the fingerprints of past megathrust ruptures. Offshore, sediment cores reveal thick layers of sand deposited by tsunamis that reached heights of up to 20 meters, matching the impact expected from earthquakes of magnitude 8.5 to 9. Yet for centuries, this segment has been eerily quiet, with no historical records of comparable disasters. For researchers, this silence is not a sign of safety, but a warning. Nuraini Rama Hanifa, a young geoscientist at Indonesia's National Research and Innovation Agency, explains that the longer the Java segment stays quiet, the more strain it builds, and that is what makes it so dangerous. Her team has spent years mapping the locked zone, using satellite data to track millimeter-scale ground movements and searching the coastline for traces of ancient tsunamis. Their work has pinned the greatest risk to this silent stretch, an area where millions now live just above sea level, unaware that the ground beneath their feet is wound tight, waiting for release. The instruments are in place, watching for the first hints of movement. Under the surface of southern Java, the instruments are recording a chorus of signals that defy easy explanation. In mid-2021, Indonesia's National Seismic Center flagged a strange, slow-moving event deep beneath the ocean. GPS stations along the coast, some perched on school rooftops and some tucked behind village mosques, began to register a subtle, creeping shift. The ground moved just a few millimeters, too slow for people to feel, but clear on the screens in Jakarta. Sentinel-1 satellites orbiting hundreds of kilometers above confirmed the pattern. Their radar snapshots, taken days apart, revealed a faint but persistent bulge in the land, stretching for dozens of kilometers. This was not a typical earthquake. It was a slow slip event, a kind of silent release of strain that can last days or even weeks. At the same time, seismic arrays picked up a cluster of low-frequency tremors, soft, rumbling vibrations far below the threshold of human hearing. These tremors, often linked to deep fault movement, appeared in bursts, then faded, only to return without warning. Microquakes, barely strong enough to rattle a teacup, flickered through the network in tight clusters, sometimes just offshore, sometimes beneath the rice fields. Analysts at BMKG tracked these microquakes, watching for patterns that might hint at something larger stirring below. INSAR data from Sentinel-1 and ground-based GNSS networks captured not just the slow slip, but also subtle changes in uplift and subsidence along the coast. The ground here is never truly still. Each new data stream, whether from a satellite pass, a GPS log, or a seismic sensor, adds another layer to the puzzle. The mid-2021 transient event in particular stood out. A slow, steady motion that lasted nearly a month and stretched across a wide swath of southern Java. For the scientists monitoring these signals, the message was clear. As Dr. Daryono, head of earthquake and tsunami mitigation at BMKG, put it, the signals we're seeing are not just background noise. They are real indicators of stress buildup. We need to take them seriously. 5 distinct types of geophysical evidence, slow slip, tremor, microquakes, satellite-detected deformation, and the 2021 transient, now point to a restless fault. The instruments are speaking, and their story is one of mounting tension beneath the calm surface. Deep beneath the Indian Ocean, the Sunda Megathrust acts as a massive boundary where 2 tectonic plates meet. The Indo-Australian plate slides under the Eurasian plate at a steady pace of 5 to 7 centimeters per year. But this movement is anything but smooth. Along the fault, some sections are locked tight, refusing to budge, while others slip quietly past each other. Scientists call these stuck areas locked patches, and the moving ones creeping patches. Locked patches trap strain like a loaded spring, while creeping patches release it gradually, preventing large earthquakes in those spots. The Java segment is dominated by locked patches. GPS and satellite data show that the plates here barely move relative to each other, storing up energy over centuries. This is why the segment is called silent. not because nothing is happening, but because the tension is building out of sight. When enough strain accumulates, the fault can rupture in a single violent release, a megathrust earthquake. The longer the fault stays locked, the more powerful that release can be. Yet the fault is not uniform. Its surface is rough, shaped by ancient seamounts, ridges, and changes in rock type. These features create asperities, areas that are especially strong and prone to locking. Asperities act as anchors, holding the plates together until the surrounding stress becomes overwhelming. When rupture finally happens, these zones are often where the largest earthquakes begin. Between asperities, smaller patches may creep or slip slowly, sometimes producing slow slip events and tremors detected in recent years. The physics behind this behavior is described by what scientists call rate and state friction. In simple terms, the fault's resistance to slipping depends on how fast it moves and the conditions at the plate interface, like temperature, pressure, and the presence of fluids. High pore fluid pressure can weaken the fault, making it easier for slow slip or even a full rupture to occur. This complex interplay explains why the Java segment can remain quiet for centuries, then suddenly unleash a devastating earthquake. Every new data point, whether from a GPS station onshore or a satellite pass overhead, feeds into models that try to capture this hidden process. By mapping where the fault is locked, creeping, or loaded with strain, scientists can estimate which sections are most likely to break next. The signals now coming from beneath Java tell a story of a fault under growing stress, shaped by friction, locked asperities, and the slow, relentless push of the plates below. Forecasting the next major earthquake beneath Java relies on a careful blend of data and probability. Indonesian and international scientists have pooled GPS readings, satellite radar, and decades of seismic records to build ensemble models, statistical frameworks that simulate thousands of possible futures for the fault. These models do not offer a countdown or a guarantee. Instead, they point to a period of heightened risk between 2026 and 2032. This window stands as a forecast, not a fixed prediction, grounded in the best evidence available. The models begin with coupling inputs, how tightly the tectonic plates are locked along the megathrust. Along Java's southern coast, GPS stations reveal the plates are nearly stuck, with little movement to ease the accumulating strain. High coupling feeds directly into the models, indicating the fault is primed for a significant release. Scientists run the ensemble repeatedly, adjusting variables like strain rates, the size and shape of locked segments, and the timing of past ruptures. The result is not a single answer, but a range, a spread that captures both what is known and what remains uncertain. Some scenarios show the fault holding out for decades longer. Others allow for an earlier rupture, even before 2026 if certain stress thresholds are crossed. Most cluster around the late 2020s to the early 2030s, matching the current slip deficit and the paleoseismic record. But the spread is wide. As Professor Fauzan of Andalus University explains, the 2026 to 2032 window is a forecast, not a prediction. It is based on the best available data, but there are still many unknowns. Key limitations shape this forecast. The models depend on GPS and satellite data, which are dense on land but sparse offshore. Coupling coefficients and slip rates are estimated from indirect signs, not direct measurements. The fault's true behavior may hinge on factors like deep fluid pressures or hidden seamounts that remain out of reach. Each run of the ensemble produces a slightly different outcome, and the range reflects the uncertainty at the heart of earthquake science. For those living along the coast, the message is clear but not absolute. The risk is elevated in the coming years, but the exact timing remains uncertain. The ensemble forecast is a tool for preparation, not prophecy. A rupture along the Sunda Megathrust south of Java would unleash a force almost beyond imagination. Scientists modeling the scenario describe a magnitude 9 earthquake, powerful enough to shake the entire region and trigger landslides far inland. Within minutes, the seafloor would heave upward, displacing billions of tons of water. A tsunami as high as 20 meters, taller than a 5-story building, would race toward the coast at highway speed. The first waves could reach southern Java in less than half an hour, giving little time for warning or escape. Cities like Cilacap, Pacitan, and Pelabuhan Ratu sit directly in the path, their low-lying neighborhoods and fishing ports exposed to the full force of the surge. Inundation maps show water reaching several kilometers inland, engulfing roads, homes, and fields. Even major urban centers farther north, such as Yogyakarta and Bandung, face intense shaking and infrastructure collapse. Across the region, millions of people live within the potential impact zone. For coastal communities, the difference between survival and loss could come down to minutes, the time it takes for the earth to move and the sea to follow. Indonesia's early warning system is built around BMKG, the national agency responsible for earthquake and tsunami alerts.